Okay. So continuing on with the switch mode supplies, we're going to jump into the boost converter. The idea and some of the design of it share similarities to the buck converter that we covered last week. Where the only difference being, instead of running like the buck converter that took some V in and brought it down, boosts, we step up. And like we mentioned the last time, because your power in has to equal power out, minus efficiency. With the buck, we were able to achieve bringing the voltage down, but having an increased current. However, with the boost, we see the opposite. Because we are increasing our voltage, our available current will be less than our input. Just because P equals IV, if we have larger voltage, we obviously have to compensate by having a lower current available at our output. So the topology similar. We use the same components that are seen in the buck. So we have our in and our load on the out. So again, we use the same inductor, capacitor, a MOSFET, and a diode. It's just arranged in a different fashion, such that we're able to now store energy in a different style and use that to our advantage to increase our voltage. So again, it's all dependent on how we control our MOSFET here, whether we send it 1 to be active or 0 to be off. Toggling our MOSFET is how we achieve our different operations and how we can change our voltage level. So to start, when we send a 1 to our gate, so our MOSFET is active, i.e. acting as a closed switch. Our current path is just within our front half. So unlike the buck converter, when we sent a 1 on the buck, our current path was the full length going through our load. But with the boost, when we send a 1 and close our MOSFET, we are restricting our current path to remain within the buck converter. So at this point, our load still sees nothing. And while we're in this state, we are, because we're sending current through our inductor, like we have seen plenty of times now, it's going, we're storing we're storing energy because we're passing current through the inductor. We're storing magnetic energy. Jeez. So we get that voltage spike and the slow current pull up. And with this, the characteristic of the voltage spike is what actually helps us in our boosting capabilities. As if we now send a 0 to our gates, our current path is now through the entire device, and we will now see our load will now receive power because we have now opened our switch, so we're blocking current through here, so its only path is to remain through the full system. Questions so far just on the topology, the layout of a boost? Nothing? Well, then our output voltage, again, when we're in the ideal state of the boost, we get our output being related to our input divided by 1 minus our duty cycle. Because this time, since our output gets power when we're sending a 0, it's not going to be directly related, or it's not increased along with our duty cycle, unlike the buck, where we saw that our output was directly just a multiplier of our input with the duty cycle. This time we're basically taking away from the full 100% to achieve what our output voltage relation is. So that is if we are sending a, let's see, call that a 30% duty cycle. Our output will be whatever input we have, 1 minus 30%. So it's actually going to be about 70% of our input.
If the voltage depends on the duty cycle, how do we pick out the inductors and the capacitor? Or is
Yeah.
that, yeah.
Yeah, no, um, that's great. It's similar to how we saw in the buck converter. Um, that was the effect of. I mean, I'll get into this as well. There's slightly different equations. Um, this CCM versus DCM mode. Um, how we always wanted to be in CCM because that's operation properly. Um, and it is all. It can be related to our our inductor and capacitor. Same with our switching speed. All of that is dependent on LNC. Very similarly, the boost converter, relatively same parameters or behaviors, rather. Um, any other questions on our output voltage relation? Does it make sense why it's not taking the duty cycle, but rather subtracting it from what a 100% duty cycle would be? What else do I have on this? So when we look at our sending zero, so when we're actually outputting power, what we can see is again. So while we are our MOSFET is while our MOSFET is active, we were storing energy in we were storing our energy inside of our inductor. So we were slowly building up current. But as soon as we switch our gates, we send a zero, so we now allow this current path. What we see in inductors is how they don't like this change in current, which results in large voltage spikes whenever they are switched on and off. So we were to say we have 12 volts. If we say have 5 volts and we're wanting to achieve 12 volts, this voltage, the voltage spike is what is allowing us to send a greater than 5 volts through our system. While again, our capacitor, it does the opposite. It doesn't like our voltage spikes. And the capacitor will tame out these large voltage spikes too drastically because they're because they don't like the instantaneous change in voltage. But when we are switching at such a speed that the capacitor doesn't have the capacitor doesn't have time to fully discharge, we'll be switching it on and off when our voltage may still be at this point. So it's not going to be able to slow down that voltage as much as it normally would. So instead of absorbing all of that transient and nullifying, what we see is our output voltage climbing a little bit above whatever our input sent was. Again, in our application with the car, since we have a system that is over 100 volts, it's not as likely that we would use a boost converter because it's much more efficient or easier to just take our large 168 and bring that down to whatever level we have, especially since in our car we only have to deal with 12 volts or lower. So for us, it makes more sense to only be running buck converters instead of bringing this down to 12 and then maybe pulling it back up to some level. So it works out that we don't need to use the boost converter in our car for various reasons, because we designed a system around not needing greater than 12 volts and the ease of being able to just pull down from our already 168 volt.
If you were to boost the 168 volts to some higher voltage, up to whatever it may be, 200, 250 volts, would the benefits in efficiency running a higher voltage tractive system, would those outweigh the inefficiencies in the converter? Or would...
Most likely not, because like our efficiency, it is some 85 to 95%, whatever most claim. But since we are also losing current, so if we had some 200 amps with that, we are going to lose to whatever the power comes out to be. If someone wants to quickly do that math so I don't have to. We will lose current, which is more required for our system, since the torque and everything is more relevant to our output current. That's how we are actually able to achieve our power through a motor. So we lose current as well as already losing that little bit of power. I don't think there's any beneficial reasons, especially because once you start to get to higher voltages, you start to see more losses if you're not doing more efficient systems like using transformers or any of those style. Any of those kind of systems.
If you're gonna run the whole tractive system through a boost converter like that, it's gonna have to be super fat, with like so much, like 80 kilowatts running through it, it's going to be probably bigger than, or as big as the inverter, maybe not, maybe bigger. So like you might as well just reconfigure your battery pack to be a higher voltage already, and then reap the benefits there instead of converting it to a higher voltage through a DC-DC.
Would it be safer at all running a boost converter if you were to say run some lower voltage, boosted up high for your tractive system? But then if you ever run into some sort of fault and the shutdown circuit kills the tractive system, then you only have 168 volts instead of 250, 300 volts in your tractive system.
Yeah, I'd say so. That's a good insight. I don't think that it's worth it, though, to put in that extra component, which is going to be really expensive, generate a lot of heat. It's going to have to be ultra efficient if you're running all your power through it, and have that extra power electronics in there just for that reason. What you can do is have, if that's a concern, which is a really important one, often, and we're not allowed to do this anymore in our competition, but for our maintenance plugs that separate the segments of our battery, often in the past in some other cars, they are like energized contactors. So like in between every little 100 volt segment is a contactor that is energized when the car is on. And then the shutdown circuit activates and opens all the main contactors, and then all of those ones in series with every 100 volt segment open as well. So like your tractive system is no longer 168 or 200 or 300 or 600 or whatever. It's now little chunks of 100 volts that are harder to hurt you.
Yeah, so the design of trying to run your system through the boost probably wouldn't be any way beneficial, because like if we still have this setup, 160 up to 250, 200 amp, you're still going to be able to pull 130 amps through your lines. So that means whatever you have in your path has to be able to withstand 130 amps still, which just makes for thick wires or excessive heat sinks and proper copper bus bars on a board to be able to withstand that. Any other questions on the setup or use case?
At what point do you switch from this style of boost converter to something like a transformer?
Great question. Something I've never looked into. I don't think I have a proper answer to that without just bullshitting something. But I would more base it on current consumption. Or actually, yeah, just general value rated voltage and current ratings of components. Because as you increase your voltage ratings and current ratings on all of your components, they just get more expensive and larger. So there becomes a point when you're trying to bring 100 volts up to 400 volts, even if you're not pushing much current through it. To be able to withstand the voltages, your components are going to get more expensive and larger, where a simple transformer could cost you significantly less. But I don't have an answer to what range would actually decide when you switch over.
Aren't transformers more oriented towards AC systems, whereas boost converters are typically more DC.
Yes, but if
Yes.
you're doing an up conversion, you can switch your DC so it looks like an AC waveform and then use a transformer to basically boost the voltage.
Yeah.
Yeah. So Braden's exactly right. And then what Steven said is you basically invert your DC to AC and then transform it and then rectify your AC to DC back on the other side. So there's a bunch of stuff you have to do if you want to do that.
Would you see excessive power losses having to convert to AC, then go through a transformer, and then convert back to DC again, as opposed to just going through a boost
Probably.
Yeah.
converter? Oh, okay.
It's how most like isolated DC-DCs work. I'm not sure exactly what the efficiency loss is. I'm sure people have designed some pretty efficient ones.
I mean, I've seen ones where they're like 85 to 90 for going from like 30 volts to the hundreds of volts.
How much is it?
What do you mean cost-wise or wattage-wise or what? Hundreds of dollars.
Nice.
But that's kind of what you have to do when you need really high voltage. Because I think there's an upper limit to boost, but I'm just not really sure when to do that kind of switch over.
Yeah, I think like if you want to pass current, like a decent amount of power output, boost is probably the way to go. Do you need a lot of current on your high voltage outputs, even for example?
Yes. Like 50 watts at the output, roughly.
But like at kilovolts, that's what, milliamps?
Yeah, so on the output, I guess it's not that much current going out.
Yeah, that's worth further Googling that I cannot provide. Yeah. But yeah, there's bound to be some switchover limit from more based on the currents. When to go from boost to start using the more sophisticated transformer style setups. But yeah, to that, I guess it is. If we're to now actually consider what our output current is, again, we're going to see our 1 minus our duty cycle relation by whatever the average current through our inductor is. Because again, we're switching this on and off at whatever duty cycle, whatever frequency. Our inductor's current waveform isn't going to have time to fully charge up, discharge, because we are switching at kilohertz to tens of kilohertz typically. What we will see rather is more of a ripple, similar to how the buck converter had was also running on the ripple. And we can consider, just look at our average. That's what we actually care about. That's smooth enough that we don't need to go into higher calculations to figure that one out. And to and our average current across that is going to be related to whatever your switching period by your output voltage, 2 times your reductance, dB minus 1. So how much current and in turn voltage you're able to output is going to be related to how fast you're switching, which is also indicative of your duty, and then whatever your inductor value is dictates how much current we're actually able to supply. And again, we'll see that in some scenario, in whatever our system is, whatever we're trying to accomplish, boosting 160 to 250, dropping it down, which means we lose our max current there to be 130 amps. If we're switching at some set 40% duty cycle, we'll achieve this, let's say. We achieve some, whatever that current value is, 6 amps. And from that, we will see, again, the 2 modes, which is dependent on your current. So if your current is nice and happy, being your actual output current is going to be do I have that wrong? We remain in the CCM, or once we kind of fall out of that range. I feel like I have my notes written backwards because that doesn't make too much sense.
Sorry, which part?
Your crossover point from DCM to CCM. Output less than your average.
Yeah, I think that makes sense. Like, for example, if you drew a line through those little waves, and that was your IL average.
Yeah, I don't know why that messed me up. Because yes, obviously we have to remain. We can't draw more current than. I don't know. I was thinking backwards. But again, yeah. So if our output current is less than, we remain in the happy, proper CCM mode. That is, we get our output current will just be just the straightforward equation. Same with our output voltage. It'll be nice and easy, just whatever 1 minus duty cycle. So it behaves as we want it to. And then DCM again is DCM is the non-ideal state that we want to avoid while we can, because it'll be cases of Um, I don't know why I don't have the graphs of this. Basically, because it'll be the similar effect to where, except opposite, where we kind of clip. We're trying to do too much. So we're causing our system to clip at the maximum. Just like the buck converter, this is not the ideal state that we want to be in, because it loses the proper functionality that we're actually trying to achieve. And again, when we're in this DCM, we will get another ugly output voltage of something even worse than what the buck converter looked like. So again, it's desired to design your system such that you don't run in the DCM range, because very similar to the buck, you start losing the actual functionality that you're wanting to achieve, and your output current and voltage start to differ from what you're actually trying to achieve. So questions on the modes of this?
Not sure if I have it backwards, like if it's different from buck, but for the DCM, doesn't that happen when like your inductor runs out of energy before the period is done? So it kind of looks like a little triangle and then like a flat bit and then another triangle like in each period.
Deflate.
Something like that. I think it's actually like a straight line.
Yeah.
Let me put a picture in the chat from what I googled.
Yeah, because I haven't touched boost converters.
Yeah, I think it's similar to buck in the sense that you're gonna have a current output, and if it's too low, so the ripple hits 0 basically, then it's just a flat bit. That's like the discontinuous, and then continuous is just ripples around the average current, which stays above 0, and everything's fine.
Yeah, that's what I thought, but for some reason I was going against myself. Yeah, but it's the so it's the same effect that we saw with the buck, where we are running out of power. And very similar effect. It can happen if your system is trying to draw too much current. So if you were to design this such that your max only ever supposed to hit 2 amps, or if so that's proper. Or if your duty cycle is too small and you just run out of power before you basically drain all of the power through the inductor before switching again. So this is how this was the behavior with the buck as well. Yeah. Basically, if you're only on for 10% of the time, something small, you're more often going to have your current through the inductor run out before you hit another switching cycle. This varies depending on your kind of power range or your load demand. Because basically, if you are trying to draw only minimal current and you're having this small ripple, you're more likely to hit this DCM mode where you don't have the effectively enough power to run through it. So again, very similar to the buck, this is a mode that we don't want to go into because of how much it fucks with your output voltage and your current as well, no longer what you ideal. So we avoid that while we can. What else do I have? Yeah, I mean, we can also very typically see our systems have feedback, just like how we saw in the buck. You'll often see voltage divider on your output coming back into your system because because again, we can similarly represent it as how we did with the linear regulators, where the internal of your device is actually going to be something with an op amp and your reference voltage switching to control that MOSFET. So we often will see that feedback line coming from our output, just like we did for the buck converter. Any questions on all of it? Any of it? Okay. This is basically all I had on the system, on boost converters. Little less prepared because, again, they're not something that we typically deal with in our system because of the system of the car. Makes much more sense to keep to design such that we have our highest voltage in the car to run our systems, and all of the lower powered stuff can more easily be driven from stepping down, opposed to bringing it down to a low voltage and boosting it back up to a mid voltage. So that is basically all I have for the boost. So any questions at all?
When do you use a buck boost?
I very specifically did not want to get into buck boost, because I personally have hardly looked into them.
Okay, that's fine.
What was the question? I missed it.
When to use the buck boost?
Oh, that's an interesting sort of philosophical question.
I think like one application I know is like from the charger, like the power bank. Like many power bank use that as a charger. Like the step, I don't know. I think I read it somewhere, but I forgot. But definitely that you boost in the power bank. If anybody know, he can elaborate this. But yeah,
I have also read about that, I think, but I'm not sure why exactly they use it. It might have to do with the voltage of the batteries being like centered around the output voltage that you want. But I'm not really sure how that works.
yeah. I think like you like the battery cells, and then they step down and then step up. I think so. Like for different application, I think so. Like I think like different phones or something, they have different voltage, so that's why they use that. But that's just purely, I guess.
Yeah, I'd say so. Like for example, you have a 36-volt battery, and you have like a input supply of like 30 volts maybe. Maybe your battery is discharged down to 28, so you're bucking down to maintain a constant current, and then that's voltage is constantly increasing as the battery charges up in voltage to maintain the constant current, and then you hit your max voltage of 36, and now you've boosted up to 36 to keep the float voltage constant in CV mode, and so your charger has to have really good control over its output voltage to make sure it can do both the constant current portion as the battery voltage rises, and then the constant voltage portion once it's settled at max voltage.
Okay, that makes sense.
But yeah, buck boost is cool because it's like 2-in-1. So you just kind of mush together the buck and the boost circuits, and you get a buck boost, and it's like, wow, that's circuits.
Other questions?
When do you use the converter or your switching thing as a gate controller for an external MOSFET versus having an internal MOSFET?
Just having a chip that has an internal MOSFET versus when you want an external. That would that'd be more dependent on power ratings, because you can imagine if your chip is only going to, if you have such a small package component, the internal MOSFET of it isn't going to be as it won't have as high as a power rating as you can achieve with getting an external, purely based on package, heatsink and all of that kind of important structure to withstand higher power, higher current. So I think it becomes when more on your power level. If you're only going to be drawing sub 1 amp, you're probably most fine to get away with a buck that will have an internal MOSFET. But once you start to get to multi-amps, multi-tens of amps probably it is, it'll be recommended that you go for a external. One final question from someone that hasn't spoken yet. Do I have to start calling people out? Elena, all of this makes sense to you? No questions?
Yes, except for one thing. Can you go over again why for when we have a boost converter, your V out would be VI over 1 minus duty cycle, not just over duty cycle? Do you know the formula I'm talking about?
Yes.
It was like kind of at the beginning.
Yeah. That's because our current path that actually goes to the load happens when our switch is off. So it's inversely related to our duty cycle, because when you talk about your duty cycle, you talk so when we say we have a 30% duty cycle, we're going to be on for 30% of one cycle. So if we're on for 30% of the time, our on time is what goes through our front half of the buck, leaving no power to the output, to the load of our buck. So we want to consider it in terms of its off time. So we want to actually look at what our off time is. So the 100%, the 100% of our duty, minus our actual on time, because we want to look at what our off time is, because that's what actually dictates the current flow through the output.
Okay, gotcha. Thanks.
Okay. Anybody else, just for the fun of it, want to have anything?